Hello. In the previous lecture, we learned about rings, subrings, and ring homomorphisms. Today, we are going to start with ring isomorphisms. In general, in mathematics, whenever we have two objects, A and B, we view them as the same things. If there are bijections between them, let's call them F and G, if these bijections preserve the structures of these objects, so we often call them homomorphisms, and at the same time, these bijections are inverse of each other. So if we have such a thing, then we view A and B as the same object, Now, you've seen this point of view in linear algebra when you were working with vector spaces. You've seen isomorphisms. So in that case, we say F and G are isomorphisms, and we view A and B as isomorphic. So you've seen this in groups as well. Now we are going to use the same point of view for rings as well. Sometimes we get lucky and we only need to have one direction for the definition. For instance, in groups, you've seen that if there is a bijective group homomorphism from one group to another, then the inverse function is automatically an a group homomorphism as well. In vector spaces, it's the same, that you've seen that if there is a bijective linear map, then the inverse map is also a linear map. We start by showing the same property for rings. Notice that this is not true for all the objects in mathematics. For instance, if we start with two topological spaces, whatever that means, if you didn't have topology yet, if you haven't had topology, forget about the sentence. But when you learn about it, you will learn that if I have a continuous bijective map from one topological space to another one, it does not imply that the inverse map is going to be continuous as well. In any case, let's show that for rings, this is true. So meaning, if F is a bijective ring homomorphism, then its inverse is also a ring homomorphism. The proof is actually rather easy, but let's go through the argument and make sure that we know how to show this statement. So what does that mean? We need to show that whenever we take B1 and B2, two elements of the domain capital B, then F inverse, the inverse of the function F, actually preserves addition and multiplication, and that means we need to show that F inverse of B1 plus B2 is the same as F inverse of B1 plus F inverse of B2. And the same should be true for the product. Okay, but what does that mean, that F inverse of B1, B2 is the same as F inverse of B1 plus F inverse of B2? You see, this is an element. This is an element inside A, and if our claim is that this is precisely F inverse of B1 plus B2, that means we need to show that when we apply F to this element, we are going to get B1 plus B2. This is what we need to show. And this is exactly what I've written over here, that when we apply F to F inverse of B1 plus F inverse of B2, we are going to end up getting B1 plus B2. And the same is true for the other equality. So we need to show that F of F inverse of B1 times F inverse of B2 is the same as B1 times B2. So as soon as we show these two equalities, we get the claim But now I can use the fact that F is a ring homomorphism, and that means that when I apply F to this summation, it is F applying to the first summand plus F applying to the second summand. That means I'm going to get that it is F of F inverse B1 plus F of F inverse B2. And by definition of inverse functions, this is just B1 and the other one is B2. And this is precisely the equality that we were looking for, meaning this is precisely this equality that we were looking for over here. And we get the claim. The same argument goes through for the product. So what we show is that if I have a bijective ring homomorphism, the inverse function is also a ring homomorphism. So it is aligned with what I was discussing about under what condition we observe to we view two objects in mathematics to be the same. So we take it as the definition of ring isomorphism. A bijective ring homomorphism is called a ring. A bijective ring homomorphism is called a ring isomorphism. So this we take as the definition of ring homomorphisms, and at the same time we call two rings to be isomorphic if there is a ring isomorphism between them, and we denote it by this notation. Okay, so now we've seen what is the definition of ring homomorphisms and ring isomorphisms, and when under what condition we say two rings are isomorphic. Okay, now we want to go back and understand subrings a bit better. But to do so, I need to recall a statement that you've seen in group theory. Let's recall the subgroup criterion. So what was it? So in general, what is a subgroup? A subgroup is a non-empty subset of a group that forms a group under the same operation. And in group theory, you've seen that a non-empty subset of a group G is a subgroup precisely when for every two elements that I pick from this subgroup, H1 times inverse of the other one is inside H. So if I know that for every H1 and H2 inside this non-empty set H, H1 times H2 inverse is also inside H, we deduce that it is a subgroup. And let's recall that in the additive notation, if G is an abelian group, this is written like this. So if I have an abelian group in abelian setting, instead of this, we have to write H1 minus H2 in additive setting. Okay, so now let's see how this can help us to understand subrings. Now, this immediately, it's rather easy, but it is useful to have the subring criterion in hand when we want to show that certain subset of a ring is actually a subring. So what is the condition? So suppose that I give you a ring R and I give you a non-empty subset of it S, then this non-empty subset is a subring precisely when it is closed under multiplication, as I've written it over here. That means what? That means if I take S1 and S2 inside this set, their product is also inside the set. So in that case, we say this set is closed under multiplication. And it is closed under taking difference. So S1 minus S2, if Si's are inside this set, is also inside this set. So under these two conditions, we can deduce that S is a subring and vice versa. Actually, the other direction is rather easy. If S is a ring, then it is closed under a multiplication, and it is closed under taking inverse, because Sn plus is an additive group. We get the first one, and because it's a ring, under the same operation, the product should be inside S. Okay, so this direction is easy. Let's go to the other direction. So what do we need to show? The claim is that the same addition and multiplication give us binary operations on the set S. That's the first claim. And the second claim is that these binary operations satisfy properties of rings. But notice that these are the same binary operations as they are inside R. So we do have the associativity of these binary operations and the distributive property of these binary operations. Assuming that they are binary operations on the set S, these two properties are guaranteed. But why are they binary operations? So they are binary operations because of the subgroup criterion. We do know that because I know for every S1 and S2 inside this set, their difference is inside S. By the subgroup criterion, we deduce that S and plus is actually an abelian subgroup, and therefore it's an abelian group. And because S is closed under multiplication, we deduce that multiplication actually give us an operation on the set S, and altogether we get that S is indeed a subring of the ring R. Okay, this is how we can deduce the subring criterion, and it's as you've seen, the proof is easy, but it is useful. We need to only focus on what matters, meaning we need to only show that the set is closed under addition, is closed under taking difference, and closed under multiplication, in order to deduce that it is subring. Okay, so next I want to discuss image and kernel of ring homomorphism. We've seen that in group theory, these are important concepts and for group homomorphisms. In fact, you've learned about isomorphism theorems in group theory, and we will do the same in ring theory. But let's start with basic properties of image and kernel of a ring homomorphism. Okay, so let's recall again what we knew, what we learned in group theory about group homomorphisms. So whenever F is a group homomorphism, then we know that the image and kernel, both of them, are subgroups. One of them subgroup of the codomain, the other one subgroup of the domain. And because here we will be working with additive groups, because at the end my interest is about understanding ring homomorphisms, and rings and plus form an additive group. Let's write down everything in terms of additive groups. So suppose A and B are two additive groups, and F is a group homomorphism from A to B. Then what is image of F? Image of F is the usual image for functions. So it is all the possible values that F takes in the codomain of F. Okay, so that's the definition of image. And in group theory, you've seen that it is indeed a subgroup of the codomain. So image of a group homomorphism is always a subgroup of the codomain. Now, what is kernel? So kernel you've seen in group theory and also in linear algebra. So kernel of F consists of all the elements inside the domain that are killed by the group homomorphism, meaning, so kernel of f consists of all the elements inside the domain where f of a is actually 0. So this is the definition of kernel, and you've seen that in group theory, you've seen that kernel of f is in fact a normal subgroup, but here I don't care about being normal because everything is abelian, so automatically all the subgroups are normal. But what is crucial, and I want to recall, is that kernel of f is a subgroup of that domain. Okay, so now let's go to ring theory and notice that in a ring A, and when I give you a ring homomorphism from ring A to ring B, so if A and B are two rings, then with addition, they are additive groups. And a ring homomorphism is automatically an additive group homomorphism. So I can get the same properties as I have highlighted here for a ring homomorphism. In fact, we get more in the case of ring homomorphisms. This is what we are going to prove next, that if f is a ring homomorphism, then the image of f is not only an additive subgroup of the codomain, but also a subring of the codomain. And kernel of f is not only an additive subgroup of the domain, but also a subring and more. So when we say something is a subring, it implies that it is closed under multiplication. But for kernel of a ring homomorphism, we have more. We have that if I take one element inside the kernel, then any element inside the ring, if I multiply any element inside the ring by this element inside the kernel, I will be still inside the kernel. You see, this is much stronger than saying kernel of f is closed under multiplication. So this is a much stronger property, much stronger than being closed under multiplication. So this is much stronger than being closed under multiplication. And in fact, we will come back to this property when we are going to study ideals of rings. But for now, let's prove these properties. So I want to show that image of f is a subring. What does that mean? Using the subring criterion, this means I need to show, and it is enough to show, that image of f is closed under taking subtraction, and image of f is closed under multiplication. And I need to show the same properties for kernel of f and a bit more. Okay, let's start with discussing why image of f is closed under taking difference and why kernel of f is closed under taking difference. These two properties we get for free because of what we had earlier over here from group theory. So in group theory, we have discussed that image of f, we have shown that image of f and kernel of f, both of them are subgroups. So automatically they are closed under taking difference. So this means we only need to focus on proving that image of f is closed under multiplication and the stronger property for the kernel of f. Okay, so let's start by showing that image of f is closed under multiplication. So what does that mean? That means we are going to pick two elements in the image of f. Let's call them b1 and b2. And I need to show that the product of B1 times B2 is also inside the image of F. But what does it mean that B1 and B2 are inside the image of F? It means that there are value of F at some points inside the domain. So it means I can find A1 and A2 in the domain such that B1 is F of A1 and B2 is value of F at A2. Okay, so that means B1 and B2, both of them are in the image of F. Now it's rather easy to understand the product of B1 and B2. So we write down B1 times B2. We substitute what we know, meaning B1 is F of A1 and B2 is F of A2. Now we simply use the fact that F is a ring homomorphism. So here we are using the fact that F is a ring homomorphism. And therefore, it preserves multiplication. Now that it preserves multiplication, we deduce that it is F of A1 times A2, which means it is in the image of F. Therefore, image of F is closed under multiplication. Now let's show the stronger property for the kernel. So meaning, this time I pick an element inside the kernel and an arbitrary element inside the ring, inside the domain, and I want to show that the product of A and X from both sides, it doesn't matter. Here I'm not assuming my ring is commutative, so I need to show it from both sides, both directions. AX or XA, both of them will be inside the kernel of F. Okay, what does that mean, that it is inside the kernel? So this happens, this is true by definition of kernel. This is true precisely when, if and only if, value of F at this point is 0. And this is true, similarly, if value of F at X times A is 0. So I need to check if these equalities are true or not. So I focus on these equalities. I look at the value of F at A times X. I use the fact that F is a ring homomorphism and write it as F of the first multiplicative term times F of X. Now X is in the kernel. Therefore, value of F at X is actually 0. So I'm dealing with F of A times 0, and we've seen that in any ring, 0 times anything times 0 ends up being 0. So now you see that the same argument goes through when I multiply A from the other side. So this time I use the fact that 0 times anything is 0 and get the desired equality. So overall, we showed that image and kernel, both of them are subrings, and kernel has an extra property that no matter what element you pick from the domain, when you multiply by kernel, you will be still inside the kernel. And we will be using this later when we discuss ideals. Okay, so let's go to another property of groups in order to introduce a special ring homomorphism. Okay, but what property of groups? Let's start with an arbitrary group G. Then you learn about cyclic groups. What do I mean by cyclic group? Cyclic group was a group that can be generated by a single element. A cyclic subgroup means the smallest subgroup of this capital group G that contains a particular element. In group theory, you learn that cyclic subgroup generated by the element G, small g, consists of elements that are powers of G. So to be more precise, it is precisely g to the n, as n varies inside the set of integers. In fact, you've seen a stronger statement. You've seen that from the ring of integers to G, we have a group homomorphism. I wrote it like E sub G. It is like exponentiating based on G. So it is E sub G of n is just G to power n. And you learn that it is a group homomorphism. And the image of this group homomorphism is precisely the cyclic subgroup that we have above, is the cyclic subgroup generated by the small element G. Okay, so this is what we learned in group theory. Now, but let me recall here that what is G to the n. G to the n is simply G times G times G dot 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 G n times if n is a positive integer. So if n is a positive integer, I'm simply multiplying G n times. I'm raising G to power n. If n is 0, I'm getting just the neutral element. So we often write it 1 for the multiplicative setting, but as I will discuss later, I want to write it in the additive format, and then we have to write down 0. We often write down 0. But whatever the notation is for our neutral element, G to power 0 is supposed to be that one. And how about G to power negative 2? G to power negative 2, by definition, is G to power negative 1, which is inverse of G raised to power 2, which means it is G to power negative 1 times G to power negative 1 times G to power negative 1. How many times? Negative n times. Notice n is a negative number, so negative n is a positive number now. So that's the definition of G to the n. So G to the n, if n is negative, is, so if n is negative, it's better to think about it as G to power negative n, negative 1 to power negative n. So when n is negative, negative n is positive, and then this one should make sense. But as I've said earlier, we will be using what we learned from group theory in additive setting more. So let's write down this group homomorphism in an additive, in an abelian group with operation plus. So in that setting, instead of writing G to the n, we often write n times a. So the group homomorphism that we have up there in the additive notation is written like this. So it is a group homomorphism, again from integers to our abelian group A, and starting with any element small a inside this abelian group, we can get this group homomorphism that's simply multiplying an integer by a. Okay, but there is a warning over here that we have to be careful about. So this is a new multiplication. This is not a, if a, you see here, even I'm not assuming that capital A is a ring. So do not get confused between ring multiplication and this multiplication. This is a multiplication that comes from group theory. It is not a ring structure here. Here I only have an abelian group. In fact, this n is not inside capital A. It is an integer. So I have one integers at one hand and abelian groups on the other hand. I'm defining this kind of scalar multiplication between some element inside integers and some element inside the group capital A. So do not get confused between this and ring operations. Okay, now the other thing that I want to point out is that because E sub A is a group homomorphism, I do have this nice property which looks like is distribution. It's not though. Because E sub A is a group homomorphism, n plus m times A, which is precisely E sub A of n plus m, is the same as E sub A of n plus E sub A of m. So I get this nice equality that we are allowed to use from this point on, that we have kind of distribution property between integers and elements of an abelian group. Now we have seen, I mean, I've pointed out this, that we can distribute an element of the abelian group from right. Now we can do the same for distributing an integer. And this is true this time because capital A is an abelian group. So in group theory, again, you've seen that a, b to power n is not necessarily the same as a to the n times b to the n. But it is the case when the group is abelian. So in general, this is not equal to a to the n plus b to the n, but when it is abelian, this is the case. And here we are in the abelian setting, then that is why n times a plus b, which is by definition a plus b plus a plus b plus a plus b, n times if n is positive, then you can rearrange them and write it as na plus nb. So we get this property mainly because the group is an abelian. Again, the warning is that we do get these nice distributive properties. Here I wrote associativity, but I should say distributive property. Okay, so so now we've seen these nice properties between integers and abelian groups. Now that we recall these properties from group theory, we've seen these things in additive setting. Let's go back to ring theory. Now, using these properties, we can define a special ring homomorphism. If A is a unital ring, then we have a nice ring homomorphism from ring of integers to the ring capital A. So this is kind of a canonical ring homomorphism from ring of integers to A, and it gives us a sort of characterization of the ring A as well. A very weak characterization, but nevertheless a characterization. Okay, so what is this ring homomorphism? I simply send n to n times the identity of the ring A. Now my claim is that it is indeed a ring homomorphism. So this is the function that I'm talking about. So any integer n, we send it to n times the identity of the ring. Again, recall that n times identity means that it is either 1 sub a plus 1 sub a dot n times if n is positive. It is 0 if n is 0, and it is negative 1 over a, 1 of a plus negative 1 of a dot plus negative 1 of a negative n times if n is negative. So this is the definition of this ring homomorphism, E. And okay, I need to show why E is a ring homomorphism. This means I have to show that it preserves addition and multiplication. But we have already discussed that such a map is always a group homomorphism. So here is what we have discussed over here, that this kind of map is always a group homomorphism. So a group homomorphism. So this means from group theory, we already know that this function e preserves addition. That means I need to focus on multiplication. And that means I need to show that E of n times E of m, and this multiplication is within the ring A, is the same as E of nm. So again, this is the operation in A. Okay, so actually the argument why this equality is true is a bit tedious, and the proof is not very conceptual. It's case by case. You can see more details in the lecture notes. Here I will just discuss the simple case where both n and m are positive integers. So in that case, by definition, E of n is nothing but adding the identity of the ring A n times. So as I've written over here, so E of n, when n is positive, is nothing but adding the identity of A n times. And when m is positive, that's the case here, and because I'm assuming this, E of m is nothing but adding the identity of A m times. Now, when n and m, both of them are positive, their product is also positive. So in that case, E of mn is adding 1 over A, this time mn times. So the first time it was n times, the second time it was m times, now it is m times n times. Okay, so now I know kind of what E of n, what E of m, and what E of mn are. So let's look at the equation that we are looking for, meaning let's try to understand what is em times en, or what is en times em, doesn't matter. Okay, what is em times en? It is this element, 1a m times multiplied times 1a n times added. And this multiplication over here, this multiplication is done inside the ring. It is operation of A. That means I can use the distribution property. I use the distribution property of the operation of the ring. Now I distribute each one of these 1 sub a's over here, each one of these guys, each one of these terms, each one of these terms is going to be multiplied by all the terms of the other parentheses. So as I distribute them, I end up getting 1 sub a times 1 sub a, 1 sub a times 1 sub a, and so on. So I end up getting 1 sub a times 1 sub a, how many times? M times n times. And notice, 1 sub a is the identity of the ring capital A. Therefore, 1 sub a times 1 sub a is nothing but the identity of the ring A. So this means I'm getting 1 sub a, I'm adding 1 sub a mn times. That's by definition E of mn. So we got the desired equality, which means E preserves the multiplication, and therefore it's a ring homomorphism. Okay, this ring homomorphism was a special ring homomorphism. We will come back to this when we are going to define the characteristic of a ring later. Another special ring homomorphism is the evaluation map or the substitution map or substitution principle. So what is it? I've already discussed binomial ring, and we will come back to binomial ring again and rings again and again. But what I've also pointed out, and we discussed it a bit more in the discussion and problem session part of the course, is that we can view binomials as functions. There are some subtle things about it, but nevertheless, we can view binomials as functions. That means what? That means given a binomial, I can evaluate it at some value. So let's make it precise. Suppose I have a ring B. I have a ring B, and I have a subring of this ring. So A is a subring of the ring B. Now, whenever I give you a polynomial with coefficients inside the subring, I can evaluate it at an element of the larger ring, capital B. Okay, what is the baby example that what is the two example that you have to have in mind? The two example is what you have already done in calculus, meaning, so whatever polynomial I give you, let's say a polynomial with coefficients inside the rational numbers, and whatever value I give you inside complex numbers, I can evaluate, I can plug in B, I can substitute B for X, and I get another complex number. So this is an example that you have to have in mind. So I'm getting a larger ring, capital B, it's like complex numbers over here, and I pick a subring inside this, like rational numbers. And then for every polynomial with coefficients inside the smaller ring, I can evaluate it. And I denote this evaluation by the Greek letter phi sub b in order to emphasize that I'm evaluating it at the value b, or at the element b. So phi sub b evaluation means what? I give you a polynomial, and then you evaluate, you substitute b for x, and you end up getting this. Now, there is a subtle thing. Let's try to understand what this means. On this side, I'm working inside the ring of polynomials. On the other side, what I'm going to get is an element inside the ring B. So here, this multiplication is happening in the ring B. But what is easy, and I'm not going to do it, I encourage you to do it on your own, is that because of the way we have defined multiplication of groups, multiplication of polynomials, under the condition that B is a commutative ring, we can easily see that this evaluation map is a ring homomorphism. So again, I should emphasize that this is true when my ring is a commutative ring. So I should emphasize that here this is the case. Maybe I should make it white. This is the case when B is commutative. Think about it, why this condition is crucial. It is kind of, you might be able to easily see it because in the ring of polynomials, we are assuming that our indeterminate x actually commutes with coefficients a sub I. And so we do need the same for elements of P. This is one way of thinking about it, but in general, in this course, we will be focusing on unital commutative rings. So maybe you can just avoid thinking about non-commutative rings at this point. In any case, now we have this nice ring homomorphism, the evaluation map or the substitution map. And throughout this course, we will be using this map a lot. Let's see what we can say about kernel of evaluation map and what we can say about image of evaluation map. Let's start with kernel. A polynomial is inside the kernel. What does that mean? If P of X is inside the kernel of the evaluation map, this happens precisely when I evaluate P at B, I end up getting 0. So this happens precisely when I have this equality. That means B is a 0 of this polynomial. And it's not surprising that we are going back to our pseudo-historical note that there is a connection between kernel of evaluation maps and zeros of polynomials. Okay, so now what is the image? Image means I have to evaluate polynomials at B. That means we are going to get elements of this form that are kind of A linear combinations of powers of B. So it looks like this. We will show in the next class that image of evaluation map is indeed the smallest subring of B that contains both the ring, the subring A and the element B. For now.